name is Nicole. I'm a second-year computer science student at the College of Charleston, and the objective of my project was to create an open source software that converts different coordinate systems. To give you some background, you might already know a few things. The Earth is not flat, the Earth is not a pear, but the Earth is also not a perfect sphere like you might think. It's actually irregular and ellipsoidal. Because of this, we have what's called different geodetic datums. Think of it as a starting point that defines the size and shape of the Earth. So say you're telling your friend how to get to your house. You might say, start at Walmart, go over the mountain, and then walk 50 feet left to my place. That Walmart that you started with, that's your reference point, that's your marker, and so that would be like your geodetic datum. These take into account the size and shape of the Earth, and therefore there's hundreds in use around the world just because the Earth has changed its shape over time. Some of these include WGS84, that's a global datum, which means its reference point is at the center of the Earth. 84 stands for 1984, which is when it was created. And 83 has its reference point in North America, and the OSGB 36 has its reference point in Great Britain. These are just a few of these. There's literally hundreds of them. So my motivation for this project was that there's a bunch of problems that result from the geodetic datum. Since there's hundreds of them, you might reference the wrong one, which results in tons of errors. You're hundreds of meters off with your calculations in terms of where you logged a certain sample. That's whenever geologists share geodetic data with each other, it requires tons of conversions. If geologist A logged his latitude and longitude of a rock sample in WGS84, he might send it to geologist B, who logs all of his samples in NAD83, and thus there's a lot of heavy math that goes into those conversions, and therefore there's more room for error. These conversions must be precise because location, as I've heard time and time again from all these geologists, is that precision and location are the most important thing. The more precise, the better. And there's also a lack of open source code to develop the code for this project. CSAR was another motivation for me. They're the System for Earth Sample Registration, and they were the one who came to me with the problem in the first place, and they wanted to create a unique identifier to log all these samples, get rid of the datums, and just kind of create one unified coordinate system. So I came up with a solution to use UTM, or Universal Transmercator. It's a global coordinate system, but unlike latitude and longitude, it does not just one single map projection, and it takes into account all the geodetic datums and creates one universal system. The conversions were developed by Charles F. Kearney, and the output consists of a zone letter, number, easting, and northing. After given a zone letter and number, you can look at this map right here, and those correspond to a single square on the map. These zones are divide the Earth into 60 different zones, and each zone itself is 6 degrees wide, or a 6-degree band of longitude. The easting and northing are in meters, and easting is referenced based on the center line of a specific zone. So once you find your little square, let's just use this red square up here, you divide it hot dog style in half, up and down, and that's what's called the central meridian, and the easting tells you how much east or west you are of that central meridian. The northing is also in meters, and it's measured relative to the equator, so it tells you how much east or south you are, north or south you are of the equator. We use big decimal, or I use big decimal instead of doubles in this code here, because big decimal allows for infinite precision, whereas doubles does not. I also have a precision variable, so that right now 10 decimals behind the integer might be okay, but later it might be 50 or 60 or 70, and that's okay. You can set whatever precision you want. This is an example that I found online of a already existing latitude-longitude to UTM converter, and so I inputted two different data, and I noticed that it didn't allow you to input the type of geodetic datum you were using, and that it only gave you 2 decimal places behind the decimal. So I created a little driver to run the code, and I allow you to input, as we see here, WGS84, and down here, NAD83. Those are two datums you're allowed to input. And I also changed the precision to 20 to show you you can do that. And we came out with the exact same integer, just more decimal places, and the same zone, number and letter. And we also added a hemisphere so you can locate the zone more precisely. So the next phases involve the reverse conversion. So I want someone, say someone needs latitude and longitude, they can put in the UTM and the datum that they want, and then they can get the latitude and longitude back. Also transfer datums more directly. So someone can just put in latitude and longitude and get back latitude and longitude, and a GUI component once it's more all-encompassing. The source code is on this GitHub link if you want to view it. And I want to thank Dr. Bowering for being my research supervisor, Cesar for giving me the idea, Charles Carney for helping me with the equations. Thank you.